This example problem might represent kind of the pinnacle of the sort of calculations you should be able to make. So it's slightly mathematically rigorous, but in concept it's no different than any of the other problems. It just involves applying Faraday's law. Induced voltage is negative N d phi dt. We've seen a lot of examples where N equals 1, and this is another one of those cases. There's just a single loop of wire. And we'll add some labels to this. We'll say it has a length L, so that's the 15 centimeters. Then it has a width W, there's our 8 centimeters. And the rod is being pulled, or not the rod, the loop, I'm sorry, is being pulled at a constant 20 meters per second along the, let's say it's being pulled along the y-axis, and the wire sits on the x-axis. So as you pull this loop farther and farther away, there is a rate of change of flux. The area is constant. It's always going to be 8 centimeters by 15 centimeters. And let's see, the magnetic field. Well, when 12 amps of current flows to the right in a wire, we can use the right-hand rule. And if you point your thumb to the right and wrap your fingers around, then I guess I should draw a set of dots to say that the magnetic field points out of the page, it points above the wire, and then a bunch of X's to say magnetic field points into the page below the wire. So make sure that your understanding of the right-hand rule is consistent with the dots and the X's that I drew. Now, the strength of this magnetic field varies, right? The field is really strong in regions close to the wire, and then as you get farther away, it gets weaker. I could maybe draw that by saying the space between the first set of X's is small, then that spacing is getting a little bit bigger, and then draw some more X's here. Now the spacing is even bigger. So this is my way of trying to graphically illustrate that this is a magnetic field that gets weaker and weaker the farther away you get. I could do the same thing with the dots. So I have the spacing between dots is kind of small, so the next set of dots is a little farther away, then the next set is even farther. Oops. So you get the idea. Let me clean up the picture a little bit. In fact, I think we can say that there's a magnetic field in this region that's equal to, well, couldn't we use Ampere's law to come up with the expression for the magnetic field at some distance from a long straight wire that carries a steady current? I think we've done that before. If you need to review your notes or look at one of my previous video lectures, we get that B is mu naught I over 2 pi. Sometimes we say 2 pi r. In this case, we'll say 2 pi y, since we've already labeled this as the y-axis. Okay, so there's the strength of magnetic field. So the field is stronger down here inside the loop, maybe of average value or intermediate value there, and then the field is weakest at that part of the loop. So there's flux, right? And the flux is pointing, as we said, out of the page. But that flux comes from a varying magnetic field. All right. So back to our mathematical expression of Faraday's law here. We can reduce it to EMF equals negative, since n is 1, it's just negative d dt of the flux. But we can't just say flux is equal to B times A and be done with it. We can certainly calculate an area, 15 centimeters by 8 centimeters, but the B is not constant throughout that area. So it's best we say that the flux is the integral of B dA. So let me clean up the picture once again so I can illustrate what dA looks like. Well, dA is just a little slice of the total area, right? It's that shaded region. So dA is just length times dW. Okay, so our EMF is negative d dt, the integral of BL dW. And I suppose dW, a little bit of width, is measured along the y-axis. So there's actually no difference between dw and dy. In step 4, we substitute for b. So the EMF is negative d dt, the integral of mu naught I over 2 pi y times L dy. So a lot of these are constants. We can take them out of the integral in step 5. The EMF is negative mu naught I L over 2 pi. And then we're left with d dt, the integral of dy over y. Okay, so what are our limits of integration? So we'll say that the bottom part of the loop of wire is already sitting at a distance of y, and then we're integrating up to y plus w. So in step 6, we evaluate the integral, and we get our EMF is negative mu naught I L over 2 pi times d dt of, so the integral of dy over y is going to give us natural log of y, and then we have to evaluate that from y to y plus w. So that's going to give us the natural log of y plus w over y. Okay, not bad, but we have to take the derivative of this expression in brackets with respect to time. So let's just make some u substitution. Let's let u equal y plus w over y. And we're not just taking the derivative of that with respect to time. We've got another function, I'll call it z. We'll say z is the natural log of u. Okay, so this whole quantity in brackets is our term z. So we're trying to take d dt of z. So isn't this true? Wouldn't dz dt be the same as dz du, du dy, dy dt? So sort of like triple chain rule here. Okay, well, let's see. dz du, if z is the natural log of u, then dz du is just 1 over u. But then again, we've already defined u as y plus w over y, so 1 over u is y over y plus w. Okay, so we've got part of it. Oh, and then this one, dy dt, what's that? Well, that's just the speed with which you're pulling the loop along the y-axis. So this term is just the velocity v. So we're just left with figuring out what's du dy. Okay, so there's our expression for u. If u is equal to y plus w over y, then du dy, we can use the quotient rule. So it's going to be the expression in the bottom times the derivative of the expression in the numerator minus the numerator times the derivative of the bottom divided by the denominator squared. Okay, so wait a minute. This is just y minus y plus the, oh, so we just get du dy is equal to negative w over y squared. So we got to put this all together. We got to multiply dz du, which is this expression, times du dy, which is this expression, times dy dt, which is v. So let's see. Step 7. All right. We've got all this. Then we got them. Okay. So our induced voltage is negative mu naught IL over 2 pi. Mu naught IL over 2 pi. and then this is all dz dt. So y over y plus w, that's dz du, times negative w over y squared, that's du dy, and then times v, that's dy dt. So the negatives cancel out. I can cancel that y with the one of the y's in the denominator. So I think we get our final result. The induced voltage in this case is mu naught I, and then look, we have length times width. So length times width, and then we have velocity divided by 2 pi y times y plus w. That's it. So let's think about what this expression is telling us. One, if we put length and width together, this just says as the area of the loop goes up, the EMF should go up. So if instead of pulling a small loop of wire with some velocity, if instead we pull a larger loop of wire with that velocity, it should be more EMF. And that makes sense because it's going to be a greater amount of flux that's changing. Okay, what else does this expression tell us? Well, it says as velocity goes up, the EMF goes up. And that's for sure. If you change this from a small velocity vector to a larger velocity vector, there's going to be a greater rate of change of flux. Okay, and then the numerator says as y, let's say, approaches infinity, then the EMF approaches 0. And that should be true by the time this loop gets really, really far away. Then it's sitting in a really weak magnetic field. So this is a bit concerning. Our formula says as y goes to 0. So let's see. That last comment I made was something like this. If the loop starts out down here and we pull it away with some velocity, then eventually it's going to end up way up here, and the EMF is going to be approaching 0 at this point because now it's sitting in a magnetic field that itself is approaching 0. But what about when the loop is way back here, so the bottom segment of loop is touching the wire? See what this expression says? As y goes to 0, the EMF should go to infinity. That's a problem. However, if we look at a magnified view of this loop of wire of length L and width W being pulled upward with a velocity V, the closest it ever gets to our wire that's carrying the current of, 12 amps? Yeah, 12 amps. We'll just call it I. See, we can't get a case where y equals 0 because we measure the distance from the center of that wire to the center of this wire, and so that can't approach 0. There's a lower limit to that value. So I think we're safe. So there it is. Now if we want to calculate numerically for this exact example problem what we get, we can try that. The EMF is equal to 4 pi times 10 to the negative 7th Tesla meter per amp times 12 amps times, let's see, what was our length and width? 15 centimeter by 8 centimeter, 0.15 meter, 0.08 meter, times velocity, 20 meters per second, divided by 2 pi times, let's see, what's the maximum EMF induced? Well, I'm not sure we can complete this problem unless we were given exactly what is the radius or diameter of this piece of wire and what's the diameter for this piece of wire. So 2 pi y times y plus 0.08. So if you're really interested, you can make up some values and figure out what's this value of y minimum. So y minimum we'll say is equal to, how about little r plus big R? In other words, big R is the radius of the current carrying wire, and little r is the radius of the wire that forms the loop. So if we want, we can make up some values. We can say this one is 2 millimeter, and this one is 1 millimeter. So our y min is 0.003 meter. Okay, so let's use that. 0.003 meter. 0.003 meter. So the pi cancels out. 4 divided by 2 gives us a 2. So now we've got an EMF of 2 times 12 times 0.15 times 0.08 times 20 times 10 to the negative 7th divided by 0.003 times 0.083. Okay, grab a calculator, see what you get. So I got an EMF of 0.0023 volts. So this is not a very effective way of inducing voltage. One, we only had a single loop. Two, the magnetic field you get from a 12 amp current flowing to the right, it might be pretty strong really close to the wire, but the farther away you get from the wire, the magnetic field is fairly weak. And we have a loop with dimensions of measured in centimeters. So I wouldn't expect this would be a way to get very large voltages, right? You're going to get micro or millivolts at best when inducing voltage in this manner. But there you have it, one of the most challenging problems that we see in applying Faraday's law, but certainly doable.